Here's a tree, each node carrying a value. Two natural questions show up everywhere. First, sum the values along a path between two nodes. Second, sum the values inside a subtree. Easy once, but your boss needs both, thousands of times a second, while the values keep changing under you. Now what? Run a depth-first search and write each node down the moment you enter it. The result is a row of 22 nodes. Look at any subtree. Say the one rooted at 2. Because the DFS doesn't leave 2 until it's finished every descendant, all 10 of those descendants land next to each other. Every subtree is a contiguous block, so a subtree query is just a range query, log n on a segment tree. Done. A path can wander anywhere. Up the tree, across the root, back down the other side. Walking it node by node is linear time per query. And on a 1,000,000-node tree, that won't fly. We want polylog. So we need the path, too, to look like a range query. The question is, a range on what array? Inside a single chain, a path is trivial. It's an interval, and a segment tree eats intervals for breakfast. So here's the plan. Slice the whole tree into chains. Hope that any path passes through only a few of them. Here's the slicing rule due to Sleater and Tarjan. At every internal node, call the edge to the biggest subtree heavy. Everything else is light. The heavy edges naturally link up into chains, since each node has exactly one heavy child. Our tree breaks into 9 of them. The spine, 1, 2, 3, 4, 5, is the longest. The rest are smaller side runs. Why does this help? A light edge means the child below it has a smaller subtree than its heavy sibling, by definition. So crossing a light edge cuts the subtree size at least in half. Halving can only happen log n times. So any path crosses at most log n light edges and touches at most log n chains. For our 22-node tree, log 2 of 22 is about 4.5, 4 chains tops. Now the trick, run the DFS again, but always recurse into the heavy child first. Same array, just deterministic ordering. And look, every heavy chain lands as a contiguous block. The spine at positions 0 to 4, the next chain at 11 to 14. The subtrees, still contiguous. Same DFS, same array. One layout, 2 structures. Path from 8 to 19. The deeper chain top belongs to 19. Climb it. Interval 16, 17. 1. Now 8 is in the deeper chain. Climb to chain top 6. Positions 8 through 10. 2. Now 13's chain. Climb to chain top 12. Positions 11 and 12. 3. Both endpoints meet on the spine. Close the gap. Positions 0 and 1 for 4 intervals on a 22-node tree, each handled in log n by the segment tree. Total, log squared. And the subtree query, 1 bracket, positions 1 through 10. Same array. Done. And the values can change. Bump node 7 from 6 to 100. Just one cell of the linear array changes. Position 9, and the segment tree absorbs the update in log n. Every path query, every subtree query you might run from now on uses the new value automatically. That's the reason a segment tree, not a static prefix sum, the array isn't frozen. One DFS, ordered by subtree size. One array, one segment tree. Paths in log squared, subtrees, and updates in log. 2 queries, 1 layout, fully dynamic.